Welcome to Computer Networks. This is lecture 18. Let's remind ourselves that there is homework 8 due this week. Homework 9 is out. Homework 10 will be out probably today. And there will be a little bit of a competition for homework 10. It's basically measuring latency between different servers, and let's see if we can take the best snapshot of latencies. And what I mean by that is, if you have a large number of servers and if you're trying to understand the delays between each server, you can just do one by one, right? One at a time. Each pair, you can measure each pairwise connection one at a time. But that's going to take a long time. And that'll no longer be a snapshot. If the first measurement started, let's say, at 1 o'clock and you're done with your last measurement at 2 o'clock because you're having to measure a lot of links, this is not a snapshot, right? So if you want to call this set of measurements a snapshot, you want to minimize the time it takes to perform the entire test. So I encourage you to come up with interesting and creative ideas on how you might reduce the time it takes to perform the entire test. And we'll discuss how different students manage to reduce the time. So you had a comment?
I have a feeling I'm not going to like that assignment just by your comment on be creative.
Yeah, you don't like being creative. There's no time to be creative. Yeah. But you don't have to participate in that competition if you don't want. You can take however long it takes to do all of your measurements. And the servers will be off for only about maybe 10 days because we're going to have servers in different parts of the world because we're trying to measure the latency between different servers. All right, so going back to homework 8. Any questions? Comments? Yeah.
To be certain, we don't have to be able to demonstrate count to infinity with ours. It shouldn't be able to get count to infinity.
Yeah, you should not be able to.
Okay.
Yeah, so the question was, should we demonstrate count to infinity with the assignment, and the answer is no. We're going to try to inflict count to infinity on your routers, but they shouldn't get into count to infinity. That's the point. Any other questions? No. All right. Homework 9. Who got a chance to at least read homework 9? No one yet? Okay. Well, it's time for us to use some tools to capture some packets and analyze the packets. That's the idea behind homework 9. We're going to use this tool called Wireshark. It's a piece of software that you install on your laptop, and you can capture all the packets that are being transmitted, not necessarily just between you and the access point, but all the packets around you as well. And one of the questions asks you to plot CDF, and I thought I would just give you an example of what a CDF is. You should all know what a CDF is, right? Who has not heard of CDF? Who has not heard of CDF? That means you all know how to do CDF. Do you want me to describe what a CDF is? How to compute it?
Yes, please.
Okay, all right. In that case, let's imagine we wanted to plot a CDF of packet sizes. And using Wireshark and doing a little bit of processing, we captured, let's say, 9 packets. And these are the packet sizes: 2, 4, 4, 4, 4, 5, 4, 6, 3. So these are the packet sizes. And what we're trying to do is plot a CDF of these packet sizes. So the first thing that we do is list all of the packet sizes. So what are the different packet sizes? 2, 3, 4, 5, 6, right? Second step is to count the number of packets for the corresponding packet size. So how many packets are there that are of length 4? There are 5 of them, right? So that's what the data shows. Then you add this third column, cumulative packets. The number on this column tells you the number of packets that are of a given length or smaller. So how many packets are there of size 4 or smaller?
7.
7, right? How many packets are there of size 6 or smaller? 9, all the packets. Any question to this point? So you'll actually have to do something like this for the homework assignment. You capture a bunch of packets, and for a particular type of packet, I think I ask you to plot the CDF of the packet sizes. Once you have this data, you plot the first column and the third column. The plot would look something like that. So just by looking at the graph, you should be able to tell the size of most of the packets that you captured. How can you tell that?
It's for the biggest spike.
Yeah, so you look for the biggest spike. Right? You could also express this as a fraction, which is what's typically done. Basically, fraction of packets of a size smaller than the size that's indicated on the x-axis. What's the y value of the last point?
Should be 1.
Should be 1, yeah. It's not 1.2. Why is it 1?
Because you can't have more than 100% of the packet.
Yeah, you can't have more than 100% of the packets, and 100% of the packets are size 6 or smaller in this particular example. You can use the numbers if you want, but it's probably better to use the fraction in your assignment when you turn it in. Any questions about CDF? If you get confused, you can just go back to these slides. Sometimes it's actually, it takes a little bit of effort to interpret the CDF diagrams. But if you look at a few of these diagrams, it becomes pretty easy. All right. So today I thought I would start by showing you an example of BGP router and how to interact with it, the publicly available ones. There is a project called Route Views where they give access to the BGP routers, some BGP routers to the researchers so that they can understand how the internet traffic is evolving, how the internet paths are evolving, how many new nodes are coming up, how many new routes there are, how often the route changes, and so on and so forth. So these are all important properties of the network to study. So there is this project that provides access to some of the routers. And these routers are placed in one of the access points type of facilities that we talked about last time. So these routers are in the access point facilities. They pair with some ISPs so that they are able to receive BGP messages. And based on these BGP messages, these routers can construct, for example, their view of the internet, what the paths are to given networks, right? So you can look at the URL at the top. You can do this yourself later today if you want. And if you scroll down, there's a list of servers that they've provided. These are basically the routers. So let's try to log in to the first one. Okay. Can you read this clearly, or maybe we can make it a little bit? Okay. So it says we can use telnet. It says UI telnet. Do you see that? I can telnet to route views. You should tell me if I make a typo because it's hard to see from here. Oh, okay. I need to have the internet. So not. All right. Let's just wait. I'm basically logging into the router. Oh, it might work. Okay. What does it say? We can try to log into another server, another router. Let's see. Oh, it's working. Okay, what does it say? Username are use. See it says what username to use. Do you see that up here, right here? Okay, so I'm in. I actually don't know a lot of BGP commands, so I just looked it up just before this lecture. You can go to Google and find these pages where they give you all these BGP commands. Turns out one of the commands is show IP BGP. This is just to look at the tables that they have. Okay, if I do this. Okay, so it tells me what is the network. That's the first column, right? And second column is next hop. So if we had to send a packet from this router, or let's say the autonomous system within which this router is deployed, to that particular network, 1.0.4.0/22. We don't know exactly where that is, but let's say we had to send a packet to that network. What are the possible next hops? There are lots of possible next hops because each router is connected to a large number of routers, right? And metric tells you, the quality of the path. You can define it in various ways. We didn't really go into the detail. There's weight, and finally, what's the last column?
The path.
The path. Now, let's say this router was using shortest path policy. Which route would it pick? It's either the first or the second one, right? So this is what a table looks like. I thought I would just show it to you. And how did this router construct this table? By exchanging the information between the routers, just like what we're doing in our homework, right? Because in our homework, we're also supposed to print the routing table. And in a way, it's similar to this idea here. We have, okay, what is the destination, which is the network here, and what's the next hop, and what's the cost? We have some idea of cost, and we don't have path because we're using distance vector, but this is a path vector protocol. And I can scroll through this list, and this is going to be a really long list because it's going to list all of the networks to which it knows some paths. Right? So that's going to be a large number of networks. You can see that. For example, if this router had to send a packet to 1022.0/23, here are all the different routes. Here are all the different next hops, right? And depending on the exact version of this software, I believe this marked entry is the preferred one. Depending on the policy that's in place, I think that mark, do you see the mark on just one next hop? I think that's the one that is going to use to send packet to that network. All right, so let's do something else. So let's say we wanted to know what's the internet path from this particular router to U of H. How do we find that out? Well, we need to know what is our network address. Does anyone know the network address for us? Well, let's do this. Let's log into one of the machines here at U of H, and we can find its IP address, and based on IP address, we have the network address, right? How do I find the IP address of a machine? IF country. Okay, here's the address. Does everyone see that? Right there? Okay, great. So what we're going to do is we're going to go back to this window. And we will say show IP. I believe that's the command. Let's go to this. And yeah, so it says show IP BGP and network address. That's how you find the path, right? Okay, show IP BGP. It's pretty slow. Huh? And let's say 129.7.240.36. I put the whole IP address. And I'll also hit enter. And we'll just wait for the command to go there and for the response to come back to us. So what we're doing is we're trying to find the route from that particular router to here. Oh, there you go. It seems like it's working. Okay, let's start reading from the top. BGP routing table entry for 129.7.0.0/16. You should be able to parse that line. What does that message mean? You should be able to parse that. You should be able to understand that. Yeah, okay, good. What is this /16? What does that mean? It's the network name. Sometimes we use the word name for numbers because it's just a way to uniquely identify a particular machine in the internet, right? I have a question for you. I asked the path from this router to a particular machine, 129.7.240.36, but it seems like I'm not going to get a path to that machine. It's instead giving me a path to a network, 129.7.0.0/16. That 0.0/16 means anything in those last two 16 bytes, right? Or the last 16 bits. So why did it give me the path to a network instead of a host? I'm interested in path to a host.
That's probably the most specific path it has.
That's probably the most specific path it has. Any other?
Hops the router, goes back, hops the router, goes back, and the last router it reaches is the gateway of the network. Because that's how it gets the response. It's probably using trace route.
Okay, so
it doesn't get any response from the host.
yeah. So there were two suggestions. One suggestion was maybe this is the most specific path this router has. Another suggestion was maybe the packet only goes to the gateway router at the border of UFH network.
Well, it can go all the way, but it doesn't get.
Yeah, didn't get all the way to this particular machine, right? But if you
Well, it would go all the way. It's not. It knows how to find the entrance to that network, and then inside that network, it's that network's job.
Yeah, I mean the response won't get out. I'm not saying it won't get to the machine. I'm saying.
Why wouldn't the response get out? There's no query being sent. You're just asking it, what routes do you know?
yeah, so
You didn't ask it to send a test map.
exactly. So here we're just printing the routing table, just like in our homework assignment. We're not sending a query to UFH and say which router is responsible for this node. We're just printing a particular entry in the routing table. And why is it beneficial for routers to not have routes more specific than that? We talked about that in the class, actually.
Well, it's already got 32 paths to that general network. You have to track, just to be conservative, 32 paths to every single IP in that network, then your table is going to be ginormous.
Yeah, it's the state's explosion that we're trying to avoid. If each router had to store a path to each host in the internet, then we'd have a very large routing table. So instead, we aggregate them. We say, if you wanted to get to any IP address with the 129.7 as the first 16 bits, then you just go take this path. That's what this entry says. It's called route aggregation, right? Okay, so let's start looking at the entry. So it says paths. There's 36 of them available. And which one is the best one? It says number 32. Right? So by default, it's going to use that path. And if that path becomes unavailable, it might use a different path. I don't know everything about what it says here, but we can try to parse together. It says not advertised to any peer because this is just a router that's trying to view the network rather than advertise route to other routers. And it seems like it just prints the path. So let's try to understand one of the paths. Let's look at this path down here. So what's this path? 3356 4323 7276. Right. So let's try to find what that path is. Okay, so you're going to have to memorize this, okay? 3356. So I went to this other site that gives us a mapping from numbers to names. So what is the first AS in the path?
3356.
Oh, there you go. It tells you. So that's the first network to which the packet goes. Okay? What's the second one? 4323. So that's the second AS that the packet goes through. And what might be the third one? Any guesses? 7276. There you go. University of Houston, right? So one of you is presenting the connectivity of our network to the rest of the internet. So you could actually use some of these clues to understand what are the different paths that are available coming into UH. If you look at all these paths, they have 7276 as the last AS. So let's look at one other path. So it seems like this particular path has a different next AS, right? Because earlier we had 3356. Let's find out what 852 is. The second and third ASs are the same. But let's look at what 852 is. Oh, there you go. So that turns out that's another path. All right. So any question here? I thought I would just give you a feel for what the paths might look like in practice. So do you now know how internet routing works? So all this router needs to know is what is the next hop, right? And you send the packet to the next hop, but you decide what next hop you want to use based on the path. If you're using shortest path, you're looking for path that has the fewest autonomous systems. All right. Any questions before we move on? So in the last lecture, we started talking about IP address allocations. They're allocated hierarchically. And we said there is an organization that actually allocates the IP addresses, right, called ICANN. What actually happens is there's a hierarchy. ICANN allocates IP addresses to these regional registries. And there's approximately one regional registry per continent. So let's say you have an organization in the US and you needed some IP address, you would go to one of these regional registries. Okay. Next, so these are just tidbits about IP addresses. When you connect your laptop to the internet through UH network, how do you configure your IP address? Do you go to some setting and then specify the IP address manually? No, you don't. It sort of happens automatically. Why do you want to automate that process? First of all, it's tedious. Right? Depending on the building you're in, you might actually have to use a different IP address. You don't want to do that time to time, and as you get older, you won't be able to remember, okay, which IP address you're supposed to use. So it makes sense to automate this, and the protocol that automatically configures your IP address is called DHCP, stands for Dynamic Host Configuration Protocol, and it works roughly like this. When you bring your client up, it sends a broadcast to the local network, saying, okay, who are the DHCP servers in this network, right? And one of the server is going to receive this message because we're sending a broadcast, not to a specific node, but a broadcast. Broadcast means the packet is going to be destined to all the nodes. So one of the servers is going to receive this message and say, okay, I'm a DHCP server. And once the client gets this message, then it says, okay, I would like an IP address and rest of the configuration parameter. That's what's happening behind the scene when we connect our laptops to an access point at home or here. So even if we just have one access point at home, we're going through the same process. The laptop comes up, you associate with the access point, and the laptop says, okay, is there any DHCP server? And the access point turns out it is also a DHCP server. And then that access point says, okay, I am one of the DHCP servers. And laptop is going to wait for a little bit to see if there are other DHCP servers, perhaps. And it's going to say, okay, I need an address and rest of the configuration parameters. And the access point is going to reply to the laptop saying, okay, here's an IP address you can use. Typically, these IP addresses are private IP addresses. They're not publicly visible IP addresses. So what that means is it is not possible for somebody from the wider internet to directly connect to your laptop, because the access point that you have at home is going to give what is called a private IP address. This address is valid just within your network. Right? It's like how we come up with names. For example, we might just use nicknames or first names if we wanted to communicate with someone within this room. But if we wanted to have a much wider discussion, we might perhaps use our full names, right? So similarly, if we just wanted to communicate within a small network or a private network, it's not necessary to have these fully qualified names. We can use what are called private names. And it turns out there is a reason why this particular method of configuring our network has become very dominant now. And one of the reasons is what is discussed in this article. I want you to read this.
It was written in 2010.
Yeah.
Still haven't run out.
This is an article on CNN. You gotta trust them. All right. So basically, this article says we're gonna run out of IP addresses very soon. Okay. And there was a follow-up article in 2011. It's a little bit more nuanced this time.
So they're using IPv6. I still don't see anybody switching to IPv6.
Yeah, so we're gonna talk about that today about IPv6. Basically, the idea is it seems like there is some discussion about depletion of IP addresses, right? That's what we saw here, and you should be able to also understand what organizations they're talking about. We just discussed that, right? For example, it says the nonprofit group that assigns addresses to service providers. So remember we said allocation happens in hierarchies? It's ICANN,
Yeah.
right? The topmost organization. It's not that all the IP addresses we've run out of IP addresses. It's the addresses that are assigned by the topmost organization to the regional registries. That level of allocation, we cannot do that anymore. How about the second last paragraph? So what is this organization?
Aaron?
Yeah.
The US's regional registry.
Right. So that's our regional registry. This organization receives allocation from the topmost organization so that it can distribute these IP addresses to the networks in the US. And it turns out here are the last 5 allocations. So ICANN said, okay, these are the allocations for these registries. The first column is the network address, basically.
What does likely come from which region? Is that?
Probably Latin America,
Oh.
if I had to guess. So why were we talking about all this? Well, IP addresses, there is a fixed size to them, right? How many bits are there in the IP addresses as we've been discussing? Only 32. That's only a little bit more than 4 billion. The question is, how do we connect devices if we run out of IP addresses? Think about PeopleSoft ID we use here. Let's say we used all of the available PeopleSoft IDs. What's going to happen?
Start recycling them for people that aren't here anymore.
Add one more number, digit to it.
Yeah, so I guess there are 2 solutions that we just discussed. One is start reusing the numbers. What's the potential problem with that?
What if I read
You lose records.
Yeah, we might lose historical record, right? And what if the person comes back? I think these are supposed to be actually permanent. Even if you go away from the university and if you come back later, I believe it's supposed to be associated with you forever. So if we start recycling the numbers, we have some problem, right? And it might work to some extent. It might be a reasonable solution, for certain objectives. So the other solution that was suggested here was add one more digit. That would solve the problem. Then basically, we have 10 times more numbers, PeopleSoft IDs. But what's the problem with that approach?
You have to completely rebuild the system.
Yeah, you might have to completely rebuild the system because all of the software that's written for the existing infrastructure, they might not assume that larger address space or namespace in this case. These are perfectly fine solutions for PeopleSoft ID depletion if that were to happen. And it turns out, in the context of IP addresses, IPv6 solution is similar to the second idea that was suggested here. Basically, increase the size of the namespace. What that means is the space from which you're allowed to derive the names, you just make that larger. For example, add more bits to the possible IP addresses. And the other solution that is very popular in the internet is using something called network address translation. This is what the routers at homes do. Let's look at this network architecture that has become very dominant today. We have something called a middle box or a router called NAT, network address translation device, that connects to your ISP or to the wider internet. And you have multiple devices at homes that connect to the wider internet through this NAT box. Right? This NAT box, as we discussed just a few minutes ago, is going to assign what are called private addresses. These addresses are valid just within your network, your home network, to these various devices that you might have at home. These are local addresses that are not globally addressable because this NAT box is just coming up with these numbers on its own and assigning them to these devices. If you wanted to assign a proper IP address, you would actually have to make sure those IP addresses are available, nobody else is using it, so that is not what this NAT box is doing. It's just going to say, we'll just scope these addresses just within this private network. So it doesn't matter if somebody else is using these addresses, we're just going to assign these private addresses. Now we have a problem. Let's say we have, let's say one of the users went to the browser and said www.google.com, right? The response is going to come back to this NAT. And if you look at the destination address of the packet that's coming back from Google, Google does not know about these private addresses, right? These addresses are not routable in the internet. So Google is going to send a packet back to that 138.76.29.7 because that's the public address of this NAT box. But we still need to deliver the packet to the right user, right? So what NAT box does is when you send the packet out, it'll have to rewrite the source IP address in the packet. You can't say, okay, this packet came from 10.0.0.1. You can't say that. Why is that?
The outsider doesn't know what that is.
Yeah, because Google doesn't know what is 10.0.0.1 is, because this is not a publicly valid IP address. So you'll have to rewrite. You go into the packet header, delete 10.0.0.1 and put its IP address, which is a valid one. We only have one, but we have one valid IP address, right? So the packet is going to come back. But the packet does not say, this is a reply that should go to 10.0.0.1. It does not say that, right?
But the router can still save maybe like save some kind of information related to
Yeah, exactly. So the router needs to remember something so that it knows the destination for that packet that's coming in, right? So there are various ways to accomplish this. And one of the ways is basically to translate the port. So as someone suggested, we need some kind of table that we need to maintain, right? But even if we maintain this table, there's only one destination address for the packets that are coming in. Right? But we still need to be able to distinguish different users. But there's only one address that everyone is sharing. How can we distinguish the packets that are coming in, even though there is only one IP address? We can use ports. When we're doing our assignments, we just have one IP address, one machine. But we still manage to not interfere with each other's experiments, right? How do we do that? By using different ports. Similarly, when we have NAT, when the packets are going out, we can allocate a port and say, this user's packets are going to come in at this particular port. And when you see a packet that comes in at that particular port, you know which internal IP address does that map to. So that's the mapping that you see here. You're basically mapping source address and port number to NAT address and new port number. Here's an example that will probably make it easier for you to understand this concept. So that's the NAT box. And we have three devices behind the NAT. So let's say that packet is transmitted by 10.0.0.1. Destination, the wider internet, it's a web server. There's the port number 80, right? So when the packet goes out, you rewrite. You rewrite the source address, like what we just discussed. And you also come up with a new port for source. And you put this information in the table so that when there's a packet that comes in to port 5001, you know the destination IP address and the destination port to which you should send that packet. So let's say the reply comes in for IP address 138.76.29.7, port 5001. How should the NAT rewrite that packet? Can you tell me? So first of all, source. Should it manipulate the source field of this packet that's coming in? No. Why not?
Because it's not the source.
The question is, should you manipulate this? Maybe not, because it's not the source. And I think what you're really hinting is there is nothing wrong with that IP address or port number, right? That's the legitimate source. That's a publicly addressable IP address. There is nothing to do. How about the destination? What's the real destination?
10.001.
10.001.33.45. And that's how the packet gets back to the private IP address. So we need to maintain this mapping table somehow. And you run into the same sort of issues that you're exploring in your homework when you're maintaining these type of tables. So you create an entry when you see an outgoing packet. And eventually you need to delete the entries, right? Otherwise, someone could launch an attack, deliberately, or it could be some kind of bug that could completely use up all the RAM in NAT. Can you think of that scenario? Let's say you wanted to create a huge mapping table. Yeah, you send a lot of packets to a lot of different destinations. Then you need to create an entry, right? Does everyone understand that? Yeah. Because we create an entry when we see an outgoing packet so that we know how to rewrite the packet when it comes in. Okay. All right. This is an example of a soft state, which is a type of state that you refresh when it's useful, when it's active, and when you get rid of it when it might not be useful or when it might not be active. And the reason I use the word might is a lot of times you don't know for sure if it is useful or not. For example, you might be able to use timers to maintain soft state, but sometimes you might make a mistake. Even though a particular entry has not been used for a while, does not mean it's inactive, right? Let's say the server is taking a really long time to send a packet back. But if you're using a timer to maintain this type of state, you might flush the state. But turns out we're still using that entry. All right. So here is one interesting challenge with this type of architecture. It's how can we get client 1 and client 2 in two different homes? Let's say these are two different homes. How can we get them to talk to each other? So let's say client 1 wants to establish a connection to client 2. And both are behind NATs, and NATs have publicly addressable IP address. And client 1 and client 2, they have private address, right? And they are actually exactly the same. Is that a problem? That's not a problem. This is all private address, right? So client 1 wants to send some packets to client 2. Think back to socket programming. How are you going to do this?
Client 2 has to be expecting to hear from the someone partner.
Yeah, so the straightforward socket programming as we did earlier in the class is not going to work. Because when you establish a connection, you need to say what is the destination IP address. So what's the destination IP address? Let's think about writing a program at client 1. Remember in socket programming, you have to say what is the destination IP address. So what should I put as the destination IP address?
NAT1.
If I just do NAT1, then
They're both-
the packet gets to NAT1 and the destination is NAT1. So the NAT1 doesn't know what to do.
Need a port.
Can you rename one
Should
of
that
them
be
from
NAT2?
NAT1 to NAT2?
Okay, one at a time. So, okay.
They're both labeled NAT1.
Okay, yeah, one should do NAT2. Yeah. All right, let's fix that.
Well, you can have two fields in the header. You can have add a field in the header.
Okay, NAT2. All right, so what is your solution?
Port forwarding, specifically tell NAT2
Mm-hmm.
certain ports are reserved for this internal IP address, and if you get them, don't change them. Instead of remapping it to a different port, always pass it on to this host on the same port.
Okay, so one of the solutions is to configure NAT2 with something called port forwarding. This is most of the routers that we use at homes actually allow this type of configuration. Basically, you go to NAT2 and say, if there is any packet that comes to port 1234, send all this packet to that IP address, 192.168.1.100. So in that case, when we're writing a socket program at C1, what is the destination IP address?
NAT2.
NAT2. And what's the destination port? 1234. And when we try to send a packet to destination 128.125.124.3, port 1234, the packet is first going to get to NAT2, and NAT2 looks at its table, forwarding table, port forwarding table that we just discussed. And it says, okay, if there's a packet that comes in to this particular port, I need to forward it to this internal IP address. So that's one way. Any other solutions? So we've heard of Skype. They use peer-to-peer communication to some extent. When we install Skype, let's say on our laptops, we don't go to the router and do port forwarding.
You have a cloud service, right?
We have a
Like a server, if you send to a server, you also send receive to a server.
Yeah. So that's another solution. You could have some kind of relay in the wider internet, right? And here is one simple solution that might automate some of this. So you have this relay that's a server. So if client C1 needs to send any packets to client C2, C1 sends a message to the relay saying, hey, I need to send this packet to C2. That connection is allowed, right? Because the relay has a public IP address. Right? But if C2 is also running the same software, C2 is also connected to relay and say, send me packets if anyone wants to send any packets to me. So there is a connection between C2 and relay as well, and that's allowed. C2 can establish a connection with the relay, right? So now, anytime C1 needs to send a packet to C2, all it needs to do is send a message to this relay saying, okay, here's a packet, the destination should be C2. The relay looks at its tables, its connections, and say, okay, the destination for this packet is this particular node. Any question about this particular way of automating the rendezvous between the nodes that are behind NAT? So one solution that we talked about is port forwarding or putting these explicit tables on NAT saying if there's any packet that comes to this particular port, send it to this IP address internally. Another solution is to automate this aggregation of different connections through something called relay. So if you had to write this type of software, could you do it based on what you've learned from this class so far?
Sure.
Yeah, it should be possible, right? Relay is a server that's listening on certain port, and you write client softwares on C1 and C2, and you connect to that relay, and then you need to come up with some kind of packet structure to say here's the source, here's the destination, etc. And you send it to the relay, and the relay will send it to C2.
Doesn't
Mhm.
doesn't Skype stop using the relay once it establishes a connection between the two peers?
Yeah, so the question was, does Skype stop using relay once you establish connection between the peers? I encourage you to explore that topic. And this is a good first link that'll give you lots of other pages on which you can learn about various ways in which you could optimize this establishment of connection for clients that are behind NATs. So this technique in general is called NAT traversal. Basically, you're trying to traverse the NATs. And I think we're going to have one of the student presentations talking about what NATs break. Because it turns out NATs make things a little bit challenging for networking, right? Yeah. But there are many other reasons why NATs might create challenge in networking, and we're going to learn more about that. So one solution was to use NATs to address address depletion. Another solution is to just increase the size of the address space.
How did you eventually run out of nets?
When do you run out of NATs?
You can only have so many nets,
Yeah, but you can have billions of NATs.
Well, and if you really want to configure, you can put NATs
how
behind
big each
NATs.
Yeah.
The
Yeah.
whole multi-tiered tree.
Yeah, you could have a hierarchy of NATs actually.
That would have performance issues. That way it's not-
You might, yes.
It's probably got some scalability.
Yeah.
Well, I mean, if you're really needing that many, you're connecting that many devices, you're gonna have scalability issues there.
Yeah. All right. So other solution is to increase the size of the address space, IPv4 that we use even today most of the time. How wide is that again? How many bits? 32. So what happens if we increase the width to 128 bits?
Like 6.
We have many more addresses. Hopefully we'll never run out.
See, if nets are so good, why do we even need it?
Because
We're gonna-
as you said, NATs have drawbacks.
And we're going to talk about that.
Groups to make them work.
Yeah, so it requires a lot of work to get them to work, right? But it turns out there are some advantages to them as well. So let's leave that to our discussion. That's going to happen, I think it's maybe next week. It's next week. So one of the solutions is to increase the address space, but there has been a very slow adoption. Here is a screen that I grabbed from Google towards the end of last year. You can see which ones are IPv6, right? The total IPv6 is the topmost line. And how many of the entries actually have IPv6 addresses? What's the scale on y-axis? It's kind of hard to see.
0.3%.
Yeah, 0.3%. And what does the report on the top say? That's a report from a different site.
It says only about 12% of BGP, of routers in the global BGP network can handle IPv6.
Mm-hmm. But that does not mean they've stopped handling, those networks have stopped handling IPv4.
Yeah.
They're IPv4 v6 capable, but not necessarily only restricting to IPv6. All right. So we're going to change gears and dive into the link layer. So far we've been talking about, okay, we have a destination to which we need to send a packet. And how do we get there? How do we discover the path? How do we forward? How do we name the destination? What that means is, what's the IP address for the destination? So we've been talking about multi-hop networks, sending packets over multiple autonomous systems, multiple routers, eventually to the destination. Now, we still have a little bit of work to do even after the packet reaches the destination. Right? Let's say the packet reaches the border of an organization, you still might forward packet through a few switches or a few internal routers, eventually to the destination. And once the packet, let's say, gets to the granularity of an organization that a building is, typically you start using what is called link layer technologies, like switching, to deliver packet to the destination. For example, we might have lots of laptops connected to a single access point, we still need to be able to address a particular access point when we need to send packets outside, and that access point needs to be able to send a packet to a particular laptop when there is a packet that comes in. Right? So we realize that the set of issues that are important for this type of packet delivery is very different from the type of issues that we've been talking about when we were talking about routing, right? So here the issue is, how does a laptop send a packet to the access point while there are lots of other laptops that are trying to do the same thing at the same time? As opposed to, I have 5 different routes that might take me to the final destination. Which route do I take? Completely different. So here are the topics that we're going to cover in our discussion of link layer. We're going to quickly zip through error detection and reliability because this topic will be very familiar to you from the very beginning of the class. We discuss them in the context of a very abstract communication protocol, and just think of link layer related discussion about these topics as a concrete application of those ideas. For example, when we need to send a packet from one node to another, let's say within the same building and let's say these nodes are connected physically using wires that go through a switch, we need to make sure that we can detect the errors that occur in the packet. Right? When we send, let's say, when a wireless access point sends a packet to our laptop, and let's say the packet got mangled in the process, we need to be able to detect that. That's called error detection. And there are many ways to detect errors, and here are some of them. Do you guys remember this discussion? We had parodies and checksums that we talked about. And we also talked about reliability. So once we know that a packet got corrupted, when the packet was transmitted from one node to another, we need to be able to resend it, for example. Right? Detection is not enough. There are two different ways in which we might be able to get reliable delivery of packets. One is to tell the original source that a packet got mangled. Let's say I had sent a request to Google for a certain page, and the packet got corrupted between the access point and my laptop. I can go back to Google and say, okay, send the packet back to me. That'd be one way, right? Another way is to just tell the access point, can you resend that packet? Which one is better, in your opinion?
Asking the access point to receive it is probably a lot faster, but it requires the access point to remember stuff after it's sent.
Okay, so the answer was, if we ask the access point to retransmit the packet, we're probably going to get the packet faster. Right? We don't have to go all the way to Google. But the drawback to that approach is we're assuming that the access point has enough memory to keep these packets in its memory.
Just go. You can send it to the access point, and the access point does not have it.
Yeah, you could design a different protocol. That was the suggestion here. You ask the access point, okay, can you retransmit this? And if the access point has that packet in its memory, it's going to retransmit that. And if the access point does not have that packet, you could actually send this packet all the way to Google. So there's actually that is a little bit challenging if you think about it, because if you wanted to implement this protocol, the access point has to actually know a lot more. We can design and build these dumb access points that can just transmit a packet. You get a request to retransmit, and you retransmit if you have it, and if not, you just say, I don't know. You need a lot more complexity in your access point if you want to implement the protocol that you suggested. It'll work, but it's going to require a lot more complexity. And
Say,
here,
I don't know, and then you ask Google.
yeah. But here's the reason for
But how
complexity.
do you know who to ask if it didn't
No,
store
no,
the packet?
not it. You.
Yeah.
You know who to ask because you asked in the first place.
Yeah. So, but here's the complexity, and it's important to understand this complexity. And that has to do with how we abstract communication in layers. When we're asking the access point, we don't even need to say, okay, this was a packet, that was supposed to come from Google, et cetera, et cetera. We can just ask the access point, can you retransmit packet number 50? We can work at that level of abstraction when we're talking about a point-to-point communication between different devices. But now if you wanted to implement your protocol, which is, can you retransmit packet number 50? And the access point doesn't have it. The access point will actually have to perform what is called deep inspection to really look into the packet, saying, okay, where is this packet supposed to come from, etc. And establish maybe a network layer connection with Google. So it's a little bit more complex. It's possible, but it requires a lot more complexity at the access point, and I hope you appreciate that. Yeah, okay. So there's a set of reliability mechanism called link layer reliability mechanism. Just retransmit based on very simple information such as sequence number. Can you just retransmit sequence number 50? Can you just retransmit sequence number 70? And the other reliability mechanism that we talked about, where the signal that a packet has been lost or corrupted goes all the way to the destination, that's usually provided at the transport layer, if you recall that. For example, TCP, right? And there are different places in which we might want one versus other. We talked about how to do retransmissions. Right? Do you remember this diagram? Yeah. So if you're talking about two nodes that are connected by, let's say, connected using a switch, or let's say an access point and a laptop, and if we lose a packet, here are the different ways in which we might lose a packet, and here are the different ways in which we might retransmit. Right? So these are the different reliability mechanisms. And we actually give a name to these protocols. We call them stop and wait protocols. And one of the challenges that we talked about is we can't fill the pipe using these protocols. Do you remember that discussion? Yeah. And it's also difficult to set the timeout value. And what was the solution that we came up with? We invented a slightly different protocol. It has the word window in it. Yeah. So rather than just sending one packet and waiting for an acknowledgement, we send a number of packets, and we wait for those acknowledgements before we send another set of packets. And it allows us to utilize the link more. All right? So that's the high-level discussion of error detection and reliability at the link layer. Unlike the network layer, when we're talking about packets going from one node to another, to another, to another, finally to the destination, when we're talking about link layer, we're talking about connectivity between two nodes that can directly talk to each other. In that case, reliability is pretty simple. You just ask that node to retransmit a particular sequence number. And the mechanisms to detect errors are very similar to what we discussed earlier. Checksums, parodies, etc. Next time.